Hi, everyone, and thank you so much for joining us for our fifth webinar in our series, AI Applications in Earth System and Climate Science. This series is hosted by NOAA's Climate Program Office and the NOAA Center for Artificial Intelligence. This session today will highlight research on coastal inundation and sea level. So today we're going to see two great presentations about research at NOAA's National Ocean Service and at NOAA's Geophysical Fluid Dynamics Laboratory. The idea for this series is to feature new applications of AI and machine learning tools in research from NOAA scientists and NOAA-supported investigators. So this series will be a way to share ideas and connect with others in the field. We hope to showcase innovation by sharing cutting-edge applications of AI and machine learning to help us understand and address complex challenges. So we're also aiming to work toward answering some overarching questions in this series, like how is AI being leveraged as a tool by researchers, and how important are partnerships across NOAA, the academic community, and private industry driving advancements in AI in Earth and climate science research. So we really do want to emphasize these collaborations. NOAA scientists and programs have really strong partnerships across disciplines, across agencies, and other institutions, and we're very excited to showcase that. So to start us off, I'd like to introduce the speakers for our first presentation, and I'm going to transfer the slides to Atiye. Here you go. So first, we're going to hear about the work from the storm surge modeling team with the Coastal Marine Modeling Branch of NOAA's National Ocean Service. So here to speak with us today is Atiye Alipour, Saeed Moghimi, Fariborz Daneshvar, along with support from the National Ocean Service's Sarush Mani, and they're also supported by Argonne National Laboratory's William Pringle. So the research team today will be speaking on their work to develop a framework to generate probabilistic storm surge and flood inundation maps using machine learning and cloud computing systems. Thank you so much for being here. We're really happy to learn about your research today, and take it away.
Yeah, thank you very much, Clara, for the introduction. Just before getting started here, I just want to thank you in particular for making lots of communication in the background to make this happen, and to everybody for giving us this opportunity and attending and listening right now. Thank you very much for your attention. And as Clara suggested, today we are going to talk about our AI ML applications in tide and surge storm surge modeling and forecasting. Again, I'm Saeed Moghimi from NOS Storm Surge Modeling Team. We are at National Ocean Services Office of Coast Survey. Next slide, please. So as you know, it's really not only 2 or 3 people moving this kind of modeling portfolio that we are doing, and I'm going to talk a little bit more about that in the next slide. So we have a group of people at NOS Storm Surge Modeling Team, as you can see up top, as well as a good network of partners. And I made the partner words in red because we are really working with these partners on a at least weekly basis, and it's not really a loose collaboration. And you can see here a list of academic partners, NOAA and agency partners, international partners, and industrial partners. Next slide, please, Atiye. Atiye, yeah, thanks a lot. So at NOS Storm Surge Modeling Team, we have a few different products and services. I will start with the operational products. First and foremost, we are the developers and supporting the operation of surge and tide operational forecast system, or STOFs. Currently, we have 2 components of this modeling system in operation. STOFs 2D Global. You can see on the right-hand side on top, the blue map is basically the STOFs 2D Global region, and on below that red kind of region is the STOFs 3D Atlantic. So the three-dimensional STOF 3D Atlantic also includes inland hydrology extremes, and it is the 3D means that it includes temperature, salinity, and current variations in water depth. So it also not only give us a higher accuracy storm surge and inland effect on coastal flooding, but also potentially opens up more supporting roles for other applications like navigations and health in ecosystem health and others. Um, Currently, we also have in a pre-operational setting, more than a year now, our STOF 3D Pacific. Again, on the right-hand side, bottom, the green area is the Pacific domain in pre-operational setting, and the plan is for the next upgrade toward the end of 25, early 26. We are going to have this component also in operation. We are also engaging in a variety of different research and development projects. And today, in particular, ATA is going to talk about deep learning based bias correction right after me, and then later, following by that one, Faribor's going to talk about support of the development of next generation probabilistic surge model. This is a close collaboration with National Hurricane Center. Also, we are developing in general on-demand cloud-based kind of storm surge modeling, and Faribor is going to report to you on that. Next slide, please. Uh, Yeah, so before handing it over to Ati, I just also want to acknowledge the two main end user and stakeholders. On the left-hand side, National Weather Services, we are supporting different offices and different parts of the organization, in particular, weather forecast offices for generating their coastal flood statements during winter storms, as well as providing boundary conditions and forcing informations to National Water Center, modeling, as well as EMC, for instance, for nearshore wave prediction system. However, being from Office of Coast Survey, we are also heavily invested in supporting mariners and navigations and commercial economy at the coastlines. And with this, I would like to turn it over to you, Atia, to continue the conversation. Thank you.
Yeah, sure, Sai. Thank you so much. And my apologies. I think there is a delay between when I like push the next button and what you see on the screen. So I will try to have a pause when I change the screens. So yeah, thank you so much, everyone. I'm Etienne. I'm presenting this work today for you on behalf of many people that contributed in this work. So as you can see, the title of this work is saying leveraging neural operators for continuous bias correction of water level forecast. And during this presentation, I will explain what I mean by each of these terminologies. And as I said, we are here focusing on NOAA's global two-dimensional surge and tide operational forecast systems called STOF 2D Global, which provides real-time global water level forecast. And the hydrodynamic based model for this system is ATSIRC, and it has a large unstructured grid over 12 million nodes, and it's a huge mesh with high accuracy. So the grid resolution at coastal level around the coastal are is at around 1.5 kilometer globally, but around the US coast is something around 3,220 meters. And Staff City Global, they provide 6 hours of nowcast and forecast with 7.5 days of horizon. So while this is one of the best available global products, when we compare the water level at some observational stations with the recorded water level, we can see that there is a difference between the simulated total water level and the observed one. And the reason behind that is because when the total water level is a result of many coastal and water processes, and like considering all of those processes requires a lot of computational resources and coupling many systems, which is not feasible. So usually we simplified some of those systems, and because of that, we see these differences between the observed and the total water level usually. And so that's why we were thinking, okay, it would be great if we use bias correction frameworks to improve the accuracy of the total water level for our gridded model output product. And one of the issues that we have here, so the gridded model output, as you said, it's global, it's gridded, it's available everywhere, but the observational data that we have, it's available at some specific location. So we're looking into one like an AI or some kind of workflow that we can use and leverage to use the point observation and the bias at those locations, and basically uh, extract and estimate the bias across the gridded model output. So when we were looking into different models, we learned about neural operators, and basically we were inspired by a study that was published in the geophysical research letter 2 years ago, that they use neural operators for the on the seismology data, and they use that to predict the pattern, the spatial temporal pattern of the seismic data. So inspired by this one, we tried to leverage a neural operator and see if we can use that for our workflow. There are many advantages of using this uh, neural operator, and one of them is that, like for example, like when you train the model on hourly data, you can directly use it on 6-minute data. When you train it on a special location, like on a few points, then you can use it in different location other than those that you were trained. I mean, you trained the model and basically estimate the uh, the model output for those locations and for different resolution. If you train your model at 30-meter resolution, you can use the same model for 20-meter resolution or coarser resolution. So basically, inspired by this study, we developed Neurocast, which leverage neural operators and basically is able to learn the spatial temporal pattern of the data. So here you can see in this figure, this is a Neurocast workflow for stops to the global bias correction. We give we give the stops to the global water level forecast and some of the input and forcing of the model, and also we give some of the information about the moon and sun zenith angle as some of the information about the tide, and then we have some static information like which location we are looking and trying to bias correct. So the latitude and longitude of that specific location. Then we put it inside, like we use this as an input of the Neurocast, and Neurocast has a flexible architecture, like you can have multiple layers of Fourier neural operator and graph neural operator. So it's a stack of these two neural operators. Fourier neural operator are great for learning the spatial and time series pattern, and graph neural operator are great for learning the geometry and basically the spatial pattern of the data. So we stack multiple layers of FNOGNO. Here we are using 3 layers of FNOGNO, but it can be 5 layers, 6 layers, depending on your application. So we use this one to calculate the bias, then we add the bias to the model output, and it gives us the bias corrected model output. So to give you some ideas, yeah. So, but before that, so to test the study, to test the workflow, we looked into the specific region. We started to look into the Northeast United States. We had 20 station, 22 co-ops station at those locations. We picked those 20 stations, and we uh, left 3 stations out, like 3 stations out for the testing, and we used 17 stations to train the model. We used the data of 2021 to 2023 to train the workflow, and then we used the entire 2024 to test the model output. And these 3 stations that you can see here, like station 2, 6, 14. We use those to see what is the performance of the model at some unseen location. We also look into other location, and we wanted to see, okay, if randomly we pick 3 station out, like some of the station out, and train the model on the other ones, how the model performs. Yeah, just wanted to say, to see how the results look like. Like, for example, this is one of the result for these stations. And like you can see here, like this is one of the cycles of how the stuff to the global looks like. So the blue lines show the result, the time series after bias correction. The gray show the raw model output, like a stuff to the global before bias correction, and the dashed red line shows the observation. So like we can see that as I said, like stuffs to the globals gives us a time series for each cycle, like for more than 7 days of forecast. And like and this is before and after we implement the bias correction. So we can see at many of those stations, we can see how it improved using the neurocast for bias correcting the data, and again for some of the unseen location. So this is just an example, but to learn like and understand how it's the performance of the model uh, at different station and in general. So first we look at the overall performance of the model. Like when I say overall, I mean looking into the entire 20 stations, and we can see, okay, when I look into it, like you can see subplot A is before bias correction and subplot B is after bias correction. So we can see we like reduce and improve the overall model performance. Root mean square error dropped by more than 55%, and R square is increased around more than 17%, and we almost removed the bias. And this is for overall, but when we wanted to look into the unseen stations, we can see, yeah, we still see very similar pattern for those stations that the model seen during the training. And this is for the 2024. So we can see that root mean square error is down by very similar amounts, like around 50%, and R square, we can see the same trend for R square and bias. And so the result was when we were looking into the entire stations. But what if we wanted to look into each station by each station and see what is the performance of the model at different station? Maybe in some station we are performing better. So again, we look into the same performance metrics, and for each station we can see, okay, the green box plots are after bias correction and gray box plots are the raw model output. So we can see across all those stations we are improving the model performance. And similar way, so we are providing data for at different lead times. And like for example, we wanted to know what is the performance of the model at different lead time, and if the model is still reliable for different lead time, like at larger lead time. So using the same performance metrics, and again, green box plot shows the model performance after bias correction, and the gray box plot shows before bias correction. And we can see, okay, the model, uh, I mean, improve the model, like after bias correction, the model performance improved, and we can see it's, across all those lead times. So we can see, okay, the bias correction framework is very robust across all the lead time. So yeah, right now, as I said, like we are working on the manuscript of this work because we wanted to get the feedback from the community. And the work also get lots of attention from at NOS level. So right now we are trying to prepare the framework for the pre-operational testing, and we are thinking to expand the workflow to the full model domain. So right now, as I said, we focus on the Northeast, but we wanted to expand it, and we wanted to use more data, more of both observational and model output data. And we are thinking to enhance the graph topology and make our workflow more physically informed. And then we are thinking, now we focus on the water level, but because we think that we can expand this to bias correct other variable like salinity and temperature. So that was just an overview, but yeah, let us know if you have any question, and we will be happy to answer your question. So with that, I will hand it over to Faribors.
Thank you, Atiya. Yeah. Hello, I'm Faiboz Daneshvar from a Storm Surge Modeling team, and in the next few slides, I will talk about our collaborative project with the National Hurricane Center to develop NOAA's next generation probabilistic storm surge model. I need to emphasize that this is a multi-year ongoing collaborative work between OCS, National Hurricane Center, Argonne National Laboratory, and academic partners such as WIMS to tackle multiple issues in order to provide a fast and reliable prediction of coastal flooding during extreme events such as hurricanes. First aspect was mesh generation, which resulted in development of OCS mesh for optimal data-driven mesh generation. Uh, that combines high resolution mesh of up to 5 meter in the vicinity of a storm landfall with coarse mesh elsewhere, such as deep ocean that goes up to 21 kilometer. Our team also developed an optimal framework to generate as low as 30 ensembles instead of hundreds of perturbation of the storm track. In that way, we would be able to capture a wide range of possibilities and reduce computational cost. Uh, we also developed a probabilistic surrogate model for prediction of maximum and minimum water surface elevation, as well as timing of when these maximum or minimum water elevations might occur. The developed surrogate model based on a few ensemble members makes the probabilistic prediction and uncertainty quantification much faster and cheaper than using hundreds of ensemble members. We have developed an ML model based on KL expansion and polynomial chaos, which I call it KLPC hereafter, and use it for a spatial analysis of maximum water elevation and a spatial temporal analysis of water elevation over time, which means finding when max elevations might happen at each location. We also started exploring neurocast that Atiye just talked about it earlier, and we're going to use it for time series analysis. Next slide, please. Yeah, here I showcased a machine learning workflow for probabilistic prediction of maximum water elevation for a case study of Hurricane Florence. And it starts with obtaining hurricane track advisory from National Hurricane Center to generate an ensemble of perturbed tracks. Here we used curve of sequence sampling to perturb hurricane crosstrack, long track, maximum wind speed, and radius of maximum wind. And the figure in the bottom left shows the distribution of perturbed variables, and the figure in the middle visualizes perturbed tracks that were split into training and validation for ML model development. The corresponding water elevation simulations within the area of interest in the vicinity of a storm landfall, which is a high resolution mesh, were then used to develop the KLPC surrogate model, which is shown in the box on the right. During the KL phase, the dominant modes among hundreds of thousands of physical grid nodes will be obtained, and then during the PC regression phase, the surrogate model will be developed based on a limited ensemble members. By expanding the surrogate model from dominant KL modes to all physical computational grid nodes, we will have a surrogate model for the area of interest and can do probabilistic analysis such as different exceedance levels of maximum water elevation that is shown here. If you go to the next slide, please. We also extended this framework to work with water elevation time series to have probabilistic prediction of water elevation over time and find when those maximums is going to happen at each location. If you go to the next slide. Yes, and this probabilistic framework has been packaged as an on-demand storm workflow, which is available on Ocean Modeling GitHub repository. It's a Python package and uses a Slurm work manager, which is compatible with traditional HPC machines, and we have been using on different NOAA HPCs so far. And the workflow reads an input YAML file that defines a storm, HPC configuration, and pass to files such as fine and coarse mesh, and hydrodynamic modeling binary files. Then generates job queues for sequences of the workflow starting from downloading storm data up to the post-processing step. Next slide, please. Here is an example of probabilistic results for case study of Hurricane Florence. These are plots of probability of water level exceeding 3 feet, both from the surrogate and from the ensemble of hydrodynamic model simulations. The spatial analysis plot on the left is based on maximum water elevation, which shows which areas might exceed 3 feet threshold during the Hurricane Florence, while a spatiotemporal analysis on the right shows variation of such probabilities patterns over time. And here I'm showing 3 time slots. Next slide, please. And here is another example of time series analysis at some selected co-ops station. On the top, you see the time series of observed mean and uncertainty ranges of water elevation prediction. These plots show how much uncertainty ranges might change over time at different locations. And on the bottom, you see the probability of exceeding certain thresholds, which shows how these probabilities change over time and might not necessarily be aligned with the time of landfall. Next slide. And we also started exploring Neurocast that Ati explained earlier as an alternative to KLPC. I'm working on a model to predict water elevation time series based on some static and dynamic parameters that are shown here for 3 example points. And if you go to the next, and here are some preliminary results for a few selected points that looks promising, and I will be working to expand it to the entire area of interest and test with different inputs for multiple storms. Yep, and if you go to the next, and yes, that was my last slide. And on behalf of the team, I want to thank you for listening to this presentation, and I'll be happy to answer your questions. Thank you.
Great, thank you so much for a really great presentation. If the speakers would like to come back on camera, we can start our Q&A session, and I'll be moderating based on the questions that come into the question feature. So please feel free to start asking them now. So we've got a couple that are coming in. Our first question is, how robust are neural operators to noise or inaccuracies in the input water level forecasts or sensitivity to input errors?
So that's a great question. So right now we try to look into the data from 2021 to 2023, and we focused on the Northeast region. But Northeast region, I mean, based on our understanding, like because we focused on a specific region, so we are thinking, okay, if we expand the workflow to, like, for example, northeast, northwest or other region, I mean, we haven't looked into the performance of the model. So when we look into the extreme events and also the general behavior of the model, like during the general weather condition, whereas the extreme weather condition, we can see the model in general during the general weather condition, it's always, uh, performing great, and uh, it's very promising. But when we look at the extreme events, there are some events that maybe happened once in 3 years, or we didn't see during the training. So we can see that the model is struggling to capture. I mean, to it is still improve the model performance, but not as good as the during the general behavior. So we are trying to look into the different behavior of the model during different weather conditions. But yeah, definitely we will try to report what we can see, I mean, how we can improve it, and if we can improve that using more different observation and more model output, and see if we can capture those behaviors. But that's our observation for now.
Thank you. The
Sure.
next question is, how can we ensure the generated probability distributions for flood extent and depth are well calibrated and reliable across different scenarios?
Yeah, I'm assuming that goes to us. Yeah, so we have done sort of evaluations. For example, looking at comparing at the co-op stations and high water marks from looking at the mean prediction from the probabilistic model versus the observed data to make sure that is reliable. And we have tested it on a range of storms, more than 25 storms within the Atlantic Ocean, and we have been getting promising results. So that shows that the um, probabilistic model is making good prediction and is able to capture that patterns. Yeah.
Great, thank you, Fariborz. We have another question. Interesting that the Stoff's raw prediction was usually higher than the observation. Do you have any thoughts on the reason for that directional bias?
I can answer that, but Said, please feel free if you want to chime in. But yet, usually when we look at the observational locations, because like I think there are some datum differences, like for example, the model output, it's based on the global water level, but some of the stations, like if you look at the station model output, you don't see that differences because they are based on the local sea level. And yeah, for the gridded model output, when we look at that some of the station on the gridded model output, we can see, okay, there is an offset, and that is usually because of that datum issues, and we're trying to address those offset and bias corrected data using this type of framework. So do you want to add anything here?
Yeah, I just want to add that this investigation and the result that Atia showed today is really in progress. We are still working on that. One caveat that this data has is that during the 2 year, or it was 3 year, right, Atia, the duration. So during this time, the model had at least one upgrade. So the quality of the data that we used for training are not necessarily homogeneous. So we are already removing some of these biases that might be from the 3-year-old upgrade. So we had two upgrade at least, I think, in between. So that's why at the last slide, if you notice, we want to make sure that we do the training on a homogeneous or kind of data, and there we can we are right now having in process to have 19-year hindcast for this stuff 2D global, and we would love to kind of have the time and effort and support to do those a little bit more better investigation. But a very good point. Thanks for catching that. Just in brief, we are working on it. Thank you.
Thank you. I think we have time for one more question, and we might be able to circle back to questions at the very end of this seminar, or I am happy to share questions with the speakers afterwards. So please continue to send them in if you have questions. But for a last question in this Q&A session, is it possible to incorporate DEM uncertainties in the model for bias correction? And does it make sense to use a tension mechanism to focus on more pronounced source of errors?
Yeah, great question. So right now, as the site says, and as we showed in the last slide, so we are trying to expand the workflow, and one of them is adding the uncertainty quantification for our bias correction. So right now we are having a deterministic model output, but definitely we are trying to see different ways that how we account for the uncertainty, and we have a probabilistic model output after we bias correction, and we consider like the both uncertainty in different input of the model and also the model output after bias correction. So I hope that I answered your question, but let me know if you need some clarification. Thanks.
Yeah, I think maybe just a very quick also adds on to
Sure.
that one. Again, the last slide that Atia showed, we also want to look into how to optimize building of the graph network that we are using for, because we do like frequency kind of a Fourier neural operator, and we have graph neural operator, and graph neural operator is the one that extending especially, right? So there are still a lot of work needed to be done in order for us to make sure we are correctly extending the graph from a limited area to global model. So that for itself is a good size research project. But thank you very much. We would love to have those points and question, Clara, later on if you possibly can share it with us, and would be more than happy. and if in particular at NOAA level, if anybody has a kind of experience with the graph and how to build like topologies for graph based on physics and shorelines, we would love to see those information and learn from you guys. Thank you.
Great, thank you so much. Yes, I will be sure to pass on information from the questions to all the speakers. So thank you again for this presentation and for answering the questions. It was wonderful. I'm going to change to the second presenter now. So our next presenter will be Chinchue Gu, a postdoctoral researcher with Princeton University and working with NOAA's Geophysical Fluid Dynamics Laboratory. So as part of Chinchue's research, she works toward a project supported by the Climate Program Office's Modeling, Analysis, Predictions, and Projections Program, or the MAP program. And she's working with NOAA researcher Lieping Zhang, focused on a project on potential sea level and storm surge impacts from detecting ocean changes in processes like the AMOC. So we're really excited to hear about your work, and go ahead.
Thank you so much, Clara, for introducing me and inviting us for this talk. So it's my great pleasure to introduce our recent study on exploring multi-year to decadal North Atlantic sea level predictability and prediction using machine learning. And before I start, I would like to acknowledge my collaborators, Li Ping, Li Wei, Tom, Xiaosong, Fan Rong, Will, and Shou Wei. So as we know, sea level rise poses significant risks to coast communities due to its impact on flooding, erosion, and seawater intrusion. Therefore, accurate predictions of coastal sea levels are crucial, which hinge on a thorough understanding of sea level variability and predictability. And in this study, we focus on the multi-year to decadal sea level variations because these variations establish a background state that modulates the impact of high-frequency storm surges and tides. And recently, the North Atlantic Ocean and the U.S. East Coast and Gulf Coast are identified as hotspots for sea level change. So our study will focus on understanding the variability and predictability for these regions. So in order to understand the variability and predictability in the North Atlantic Ocean, here we apply a machine learning method called self-organizing maps, or SOMs. The SOM briefly is an unsupervised machine learning method used to cluster high-dimensional datasets. And compared to some more conventional method, it can handle nonlinear behavior, and it is not restricted by orthogonality or stationarity. And therefore, it can characterize patterns that are more physically relevant. And this figure shows a schematic for the SOM method. So the black cells here shows the SOM nodes that are initialized with random values, and the purple clouds here shows the input data vectors. And here our input data vectors are maps of the sea level anomaly patterns. And the SOM is trained by comparing the SOM nodes with each of the input data vectors and modifying the SOM nodes based on their similarity. So by doing this repeatedly, we're able to get some patterns that span the data space and represent the variability in the data. So here specifically, we apply the SOM to the 5,000-year annual mean North Atlantic sea level anomalies from two pre-industrial control simulations to characterize a full range of internal sea level variability. So these simulations include 2,500 years from the GFDL spear low and 2,500 years from the GFDL spear median models. And then let's look at some results. So this figure shows the 3x4 SOM that characterize the North Atlantic sea level variability, and these dominant patterns of variability are robust to different SOM sizes. And as you can see here, nearby SOM nodes show similar patterns and faraway nodes show different or even opposite patterns. And some of these nodes have large sea level anomalies that extend to the US coastal regions. For example, this node 3.1 have larger than normal sea level anomalies along the US northeast coast. And this node 3.4 has larger than normal sea level anomalies along the US southeast coast. And then in order to understand the mechanisms associated with the sea level variability, here we composite the AMOC or the Atlantic Meridional Overturning Circulation patterns associated with these some sea level anomaly patterns. And we found that composites of the AMOC anomalies on the sum show distinct phases associated with different sea level anomaly patterns, and some of these associations are consistent with previously identified mechanisms. For example, this node 3.1 that has positive sea level anomalies in the um, along the U.S. northeast coast is associated with a mature negative AMOC phase. And this node 1.3 that has an opposite pattern compared to the 3.1 node has a mature positive AMOC pattern. And these two dipole-like patterns 1.1 and 3.4 are associated with AMOC transition states between its mature phases. So after kind of understanding the variability and the mechanisms associated with the sea level variability, we started to wonder whether we can actually measure the sea level predictability using the SUM framework. So here we introduced this SUM-based transition probability framework. And we started by asking the question, starting from a specific node, such as the node 3.1 here, what is the probability of staying at itself, so at the node 3.1 itself, or transitioning to each of the other nodes after 1 year? And by answering this question, we can actually get a table like this. So this figure shows the lag 1 transition probability table, and the yellow box shows the original, the starting point, that is our node 3.1. And the positions of these nodes are corresponding to the positions of these numbers. So, and the reddish color shows significantly higher than normal probability, and the bluish color shows the significantly lower than normal probability. So as you can see, 1 year after starting from this node 3.1, there is still 49% probability of staying at itself. So that means a very strong persistence. And there are also probabilities of transitioning to the adjacent nodes. And in addition to the lag 1 probability table, we can also do that for the following lags. For example, I'm now showing the first 4 years after starting from the node 3.1 here. So as you can see, in the first several lags, the highest probability is still the starting node itself, which means strong persistence at the beginning. And if I move forward, you can see that there is kind of anti-clockwise transition tendency across the sum if you follow the pink signal here. Yeah, so if that means the nodes tend to transition anti-clockwise to the adjacent nodes rather than clockwise. And we believe that the persistence and this anti-clockwise tendency across the sum are likely due to the shifts in the AMOC phases. And as you can imagine, knowing where the sea level anomalies is going across the sum, either through persistence or anti-clockwise transition tendency, indicates high predictability because you know where it is going across the sum. And starting from year 18, as you can see here, the probability is more evenly distributed, which indicates a loss of predictability. And we can repeat this analysis for all the starting nodes. So what I just showed is this node 3.1, and you can see for other nodes, and this shows the lag mark. So you can see for other nodes, there are still some like persistence as well as an anti-clockwise transition tendency. And again, knowing where the sea level anomalies is going across the sum indicates high predictability. So following this logic, we can therefore quantify the predictability of the sea level anomalies over time based on the number of significant transition probabilities for each starting node at each lag. And the line here shows the number of significant transition probability averaged for all the nodes, and the shading shows the spread. So based on the global significance theory, if the line is on or above this gray line, we view the sea level pattern at that lag as theoretically predictable. So based on this criteria, we can say that the large-scale North Atlantic sea level anomalies are considered predictable for about 16 and 21 years on average for the spear low and spear high, spear low and spear medium pre-industrial control simulations, respectively. And as you can see, there are some kind of difference between these two simulations, and we think that the potential reason for this difference may be related to their AMOC variability. So this figure shows the spectral analysis for the AMOC indices in spear low and spear medium pre-industrial control simulations, and as you can see, both models have peaks at a period of about 30 years, but the amplitude of the spear medium exceeds that in the spear low. So that might be the reason why the spear medium has slightly higher predictability. So after looking into the theoretical predictability in these pre-industrial control simulation, we started to wonder whether it can these bring actual prediction scale to the historical prediction, for example. So here we apply a sum-based model analog method for prediction, and our target is the reanalysis data set from Spear, and we composite these patterns from this reanalysis data set onto each sum node, including those with time lags, as our target. And the predictions from the sum-based model analogs are the composites of the model analog sea level patterns, including 10 most similar sea level anomaly patterns from the pre-industrial control simulation from the corresponding node for each reanalysis year assigned to each node. In comparison, we also introduce a conventional state-of-the-art method, and that is calculated as the composites of the initialized decadal hindcast produced by the Spear-Low model, initialized from the same year as the reanalysis assigned to each sum node. So all the predictions are based on the sum, because in this way we're able to see how they evolve over time. So then let's look at some results. So this in this figure, the first row shows the target, and the second and third rows shows the predictions from the sum-based model analogs and the initialized hindcasts. And as you can see, this example shows the prediction starting from the node 3.1. So if you compare these three rows, you can see that the initialized hindcasts work better at early lead time, but the mod analogs actually perform better later. For example, if you compare the year 7 pattern, the mod analogs performs better compared to the initialized decadal hindcast when they comparing with the target pattern. But the prediction scale of the model analog depends on the initial condition. So for example, for this example, starting from the node 3.4, in this time, the performance of the model analogs actually fall behind of the predictions of the initialized decadal hindcast if you compare these patterns. And we can also summarize the prediction scale for all the nodes using the anomaly correlation coefficient, or ACC, that calculates the pattern correlation between these patterns. So as you can see, in general, the hindcast, which is shown in the purple line here, outperforms the model analog prediction for most nodes in the first several years. And then the spread of the prediction scale of the hindcast starts to overlap with that of the model analog prediction. Although that the sum-based model analog method does not perform as well as the decadal hindcast in general, there are still some advantage of this method, because it can provide reasonably good prediction scale over longer lead time for certain initial states. For example, this figure shows the ACC from lead time 1 year to 30 years. And as you can see, some of the initial condition, for some of these initial condition, the method can actually provide reasonably good prediction scale, as you can see here. Therefore, the sum-based analog analog method can provide a useful tool for early estimation of large-scale sea level states for certain initial conditions. Therefore, it can bridge the gap between until the initialized decadal hindcast from the dynamic model become available, because these predictions often just extend to a lead time of 10 years. So in addition to the prediction of the large-scale sea level, we also conduct prediction of the low-frequency sea level variations along the U.S. northeast coast, as shown here. And these figures shows the correlation between the low-pass filtered detrended tide gauge records along the northeast coast and the predicted time series from the initialized hindcast and SOM-based model analogs. And as you can see, the scale of the hindcast remains high, which is likely due to an accurate representation of the low frequency variability in the northeast coast. And the SOM-based model analogs initially outperformed the hindcast, but later on fall behind. So in summary for this study, here we use a SOM-based framework to identify dominant patterns of sea level variability in the North Atlantic Ocean and assess the associated predictability on multi-year to decadal timescales within the 5,000-year pre-industrial control simulation. And we found that the low frequency AMOC variability associated with the large-scale sea level patterns leads to prolonged decadal predictability that lasts for about 15 to 20 years, and it also depends on the initial condition. And we found that the cost-effective SOM-based model analogs actually allows for long lead predictions on decadal timescales. And in addition to what I talked, that is associated with the low frequency AMOC, we also identified other sources of predictability related to the slow dry circulation adjustment triggered by the North Atlantic Oscillation, or NAO, like stochastic variability, but I'm not showing today. But if you are interested in, please feel free to check it out in our paper. And because this webinar focuses on the AI applications, I will also take a moment to briefly expand on the SOM method itself. So basically, I'm going to talk about some other applications of the SOM method. So as I showed in today's talk, each input data vector for the SOM, for an ordinary SOM actually, contains a spatial pattern at a single time step. So you can think of it as like classifying individual pictures. So for example, imagine that we are classifying a set of cat pictures, and you can see that looking at this single picture, you can see this cat staying aloft, but you don't know what happened before and after this snapshot. So using this, basically I'm saying that using this ordinary SOM, we can only characterize the spatial SOM patterns. And in order to bring in the idea of the time evolution, one way is to use the transition probability framework I showed today. And in addition to this framework, during my PhD with my advisor, Dr. Melissa Gervais at Penn State, we also developed a new application of the SOM method named as evolution SOM. So using this method, we are able to classify a set of short movies instead of snapshots. So still using the same cat example, instead of just seeing the cat staying aloft, by looking at the video, you get to know like what led to the jump and what happened next. Therefore, this method can allow us to characterize the full spatial temporal evolutions, basically characterizing the variability over space and time simultaneously. And using this method, we diagnosed the two-way coupling in the decadal North Atlantic SST variability. And if you are interested in, please feel free to check out our paper here. In addition, so in a more recent study during my postdoc, we also developed some reconstructed prediction method for seasonal sea level prediction along the U.S. West Coast region and Canadian West Coast. So specifically, we reconstruct the sea level anomalies based on the some patterns and the projected time series onto these patterns. And then we are able to capture the large-scale signals while filtering out less relevant component. And finally, we are able to improve the seasonal sea level predictions along the US and Canadian West Coast from multiple dynamic models as shown on the right-hand side. So the pink bars here shows the improvement we achieved through the SOM reconstructed method. And this paper is currently under review. So, okay, with that, I think that's all for my presentation. And I'm happy to take any questions. And I'll go back to my summary slide here. Thank you so much for your attention.
Thank you so much for that great presentation. Everyone, please feel free to use the question feature to input your questions for Chinjue for that great presentation. Our first question for you is, how can the optimal size and dimensionality of the self-organizing map grid be determined for effectively representing the complex patterns of North Atlantic sea level variability?
Thank you for the question. Yeah, that's a really good question. I'll go back to my yeah, I actually have like supplementary slides for showing like different sizes of the SOM maps. So as you can see, we actually determine the size by testing different sizes of the SOM. So if you go larger, the larger SOM will give you like more of like transition patterns of the existing patterns in the 3x4 SOM I showed. So this is like a 4x5 map. So basically the physically distinct or physical relevant patterns still there, but there are just more transition patterns. And if you look at a smaller pattern, there will be like less transition patterns, but there could also be like a possibility to merge some physical relevant patterns. So that is one thing we would like to avoid. So basically it's saying that if you go larger, you can see more patterns, but it can be like unmanageable. And if you go smaller, you can merge some very important patterns like has different physically distinct mechanisms. So if you want to like choose the optimal choice, you need to like test different sizes and determine like what is the best for your purpose. So for our purpose, basically we can use like flexible like choice, like we can use like different choices, and it does not actually change our main conclusion, but you would like to like choose whatever that is best for your purpose. Yeah, thank you for the question.
Great, thank you. And we just have a comment that says, great presentation, thank you.
Thank you. Thank you so much.
One other question, how sensitive are the machine learning derived predictions to the initial state of the AMOC? And could this sensitivity inform when machine learning based approaches are most reliable? Do you have any thoughts on that?
Yeah, that's a great question. So actually, if we look at the prediction using the SOM-based model analogs, you can see like the shading is the spread of the prediction, and it's actually like kind of not that sensitive to the initial condition, but it also like depends on the AMOC states. For example, if you start with like a very extreme AMOC states, you like it, but like so the analogs you selected will learn better like where it is going, because you know it will kind of go to the neutral state. But if you started from a neutral AMOC state, it has like less knowledge of where it is going. Yeah. And I think for some of the other people's work, you may use like the different initial states to choose like how robust you can like imagine this prediction may be. Yeah, this is one like opportunity to help you to determine like how confident you should be for this prediction.
Okay, great. Thank you so much. I think for the sake of time, we'll need to wrap it up, but please feel free to reach out with any other questions for any of our speakers today. I'm just going to share my screen one last time. So thank you all again for joining us, all of the speakers and the participants. Thank you for sharing your work and for asking questions. The Climate Program Office and the NOAA Center for AI is excited to host more webinars in this series and possibly expand the scope of the series in the future. So I put a link in the chat where we will advertise any future webinars, as well as where you can find recordings of past webinars. I also put some resources for learning more about the NOAA Climate Program Office and the NOAA Center for Artificial Intelligence. And you can feel free to reach out directly to me with any questions about the webinar series or CPO or NCAI, or to reach out to any of the speakers today. So thank you so much and have a nice weekend.
Thank you so much.